So, welcome to the Biweekly solutions of LeetCode. Last week, this one happened. So, this is the first question. Find minimum operations to make all elements divisible by 3. So, and you can do the following operations: add or subtract one from any element. Then the minimum number of operations to make all elements divisible by 3. So this is actually quite easy. So, I'm not even gonna use a whiteboard for this. If any element is already divisible by 3, then we do not need to do anything for that. Otherwise, an element can be of type 3n plus 1 or 3n plus 2. 3n type of elements are already, so you don't have to quickly count them. They're already divisible by 3. And if you want to make these type of element divisible by 3, you can just subtract one operation it will take, plus one operation. And you can add one here to make it divisible by 3. So this will be plus one operation, which will be easily simply just one operation for anyone who's not divisible by 3. Anyone who's not divisible by 3 will have to do one operation to make them divisible by 3. So this is the simple solution. Let's go check. So this is the second question, and it's also quite easy. Actually, this is quite easy. It's becomes ABC or very easy. You can do all of them in less than 10 minutes. Like if you've done similar questions as well. You're given a binary array. You can do the following operation in the array any number of times. Choose any three consecutive elements and flip all of them. This will 0 to 1, 1 to 0. Return the minimum number of operations to make all the elements equal to 1 if it is possible. Otherwise, return minus 1. So that is quite easy. It's actually you can just do this quite simple. Work, right? Let's take the first example. It's 0, 1, 1, 1, 0, 1, 1. Right. So the first example is 0, 1, 1, 1, 0, 0. This way, then we want to make all elements equal to 1 and we can flip any three consecutive elements. These we can flip, these we can flip, these we can flip. So basically, we have to make one set of position, right? So we'll come from a starting and wherever it's not one, we'll try to switch it. We'll try to switch it to make it one. And then we'll see what happens to the next two people. We'll have to also think with it, right? So let's just simply try run on this and it will always work. We'll come to it now. This guy is 0 initially. If we flip this, then it will become 1, 0, 0, 1, 0, 0. Now this guy, now we flip this first three guys. We'll start a poll from starting, and whenever it's a 0 and we have not changed it, we'll try to change it. What do I mean by if I'm not changing? We'll come to it. If any guy is 0, we'll try to just make it 1, right? So that is the whole point. We have to make it 1. So from starting, if this guy is 0, we'll flip these three consecutive ones. So we flip these three. Now we'll come to a second element, 0. Now this element is again 0, so we have to again flip. So here we'll flip again. 1, 1, 1, 0. Okay. Now and 0, 0. These remains unchanged. Now we'll come from the third index. This is already one, so we don't actually have to do anything. Then we come to the fifth index, sixth index, seventh index, and or like basically all the indexes are here. We'll have to change once, right? Because this is zero. We'll change here once, then all these three will change 1, 1, 1, 1, 1, 1. So these will always be the minimum number of operations because we are making every like for each guy we are taking one operation at max. So this will be the best way to do it. Obviously. Now come to it. If it sometimes it might not be possible, we'll come to that case. And if it's return minus one if it's not possible. Otherwise, this algorithm it works fine always. Firstly, whichever problem we are having, we are fixing it right there only. So we are doing minimum number of operations. Coming from starting, if it's a 0, we'll change. So that's simple. And at the end, we can only do the operation till the index n minus k plus 1, right? If we are doing one base indexing, this is first index, this is two index, this is four index, five index, six index, seven index. K, let's say it's three here, right? Mhm. Uh, we can do it from let's say 6 minus 3 plus 1, right? 6 minus 3 plus 1, 4. From here, from till 4, we can do this operation. After that, we cannot do this operation because three consecutive elements are not there. So if after switching, last element still remains zero, you cannot change them. You can never change them, right? And if you want to change them from behind, then this guy will become one, or this guy will become zero. Let's say, let's come to a case when it's not possible. Let's see the second case simply. They've given everything in the question. There's nothing in this question actually, but complete 0, 1, 1, 1, 1, and we have to make everything one. We'll come to the first element. We'll simply do this thing. Like if it's 0, convert it to 1. But when we convert it to 1, we have to convert the next two elements also to flip also. We'll have to flip them also. Now we come to this 0, then 1, 1, 1, 3, simple. Now we can only do this operation till n minus k plus 1, as I told, if it's one base index. So we can only do this till here if you think about this, because there are not no you cannot take three elements here, right? So after doing this operation, you have to check the last elements. If any of them is zero, then it's not possible, because you cannot make this guy one by changing this subarray, because this subarray does not exist. But let's consider, but if you think like we can flip this and make this one, but then this guy will become zero. And if you want to make this guy one again, and you're saying, okay, I don't want to change this guy, but because I want to make sure this is one, so you will come here and change this. But if you change this, then the initial guy will become zero, and still this will keep on happening till the starting, till a point when in starting, if you want to make this particular guy as one, you'll have to make the starting guy zero. Then again, it won't work. So the basic thing to understand here is you can start from one side and you have to complete it from that side. You can start from ending also. That one will start from anywhere, and then you'll have to complete it till the end. If it is possible, then it is possible. Possible. Otherwise, it's not possible. Because as I'm saying, right, if I want to make this guy one, I'll have to change this subarray. Then this guy will become zero, and this guy will also become zero. Then we'll have to change this subarray, but then this guy will become zero. So basically, it will keep on happening. If it's possible, it will be possible from one side. If it's not possible, it won't be possible from anywhere. So that's the second question. The code is quite simple. We'll come to it. Okay. So the basic idea is, if this guy is zero, we'll do this in second last index, so n minus k plus. So it goes to the second last index, and just if the guy is zero, we'll flip this. We'll make it one. We'll flip the next two elements and answer plus plus. Then we'll have to check if everyone became one or not. You can just check the last two elements also in this case. That will also work, but I'll just check all. And then you can just return the answer. That should be, thank you. So this is the third question. This is actually, I would even say this is easier than the last question, but it is what it is. It's the same question actually, but in that you were flipping three elements, right? In this you flip every element from that particular suffix. You flip everyone, and so basically in this case it's always possible, and it's the same algorithm. It's the exact same algorithm. In this case, it's always possible because we don't actually have a size. Let's take the same example that it was there in last one, 0, 1, 1, 1. It will be always possible in this one because we don't actually have a size. We can click a single element also, like it at the end. It's always possible in this. Let's say it's same algorithm. If it's a 0, we'll convert it to 1. Now everyone will be flipped from here to there. So we cannot go ahead and mark everyone, because that will be order of n square, right? If we go ahead and mark everyone, then it will be order of n square. But we can simply think of this as, let's say, if operation is applied twice to a single element, then it will remain the same. If the operations are applied, let's say at this index, uh, and then at this index, then the operation is applied at this index twice, right? What does that mean? If an operation is applied twice, so 0 to 1, 1 to 0, or 1 to 0, 0 to 1. So if the operation is, let's say I'm calling it back in code, if the operation is even times applied, then the bit does not flip. We cannot go ahead and change everyone because that will be our. So, but we can simply think of this like this. If we switch this guy, everyone in the front will change once. Will change once. Right. So this will be 1, 0, 0, 0. Then we'll come to this guy. Then we'll flip everyone 1, 1, 1. We'll flip till the end, right? We flip till the end like this. So the only thing here is that we cannot actually mark them. In the last question, we could mark them. Now we cannot mark them, but we can count the number of operations applied on this particular one. That will be all the number of operations that are applied before this one, right? Because everyone, like let's say I applied the operation at ith position, let's say ith position, then all the guys at the back of it will get the same position effect. So it's very simple. There's nothing in this question. So it's the same and it's actually much easier. I would say we uh, will take a bag, or you can name it anything. Then whenever we apply an operation, we'll do back clusters. That means all the guys in the front of this will change their state. And if let's say bag module 2 is equal to 0, meaning that even number of times operations was applied. If operation is applied even number of times, then the uh, bit does not flip. And if it was already 0 and the bit does not flip, that means that this is a 0, then we need to convert it and then we'll apply an operation here. We don't need to just continue, this is okay. And we'll just do answer plus plus. Okay, we are applying an operation one. And the other case is, let's say the bit has flipped. The bit has flipped and it was 1 earlier. Because we're not changing it. The values we have is of the past, like in the starting array. We have the values of the initial array. Right. And if the value was 1 and bag is odd. Bag is odd meaning odd number of times the operation that we apply. That means it will flip. So 1 will become 0. And we have to change again, right? Because we have to make all zeros to ones. So if 1 becomes 0, then we'll have to apply an operation to again make it 1. Back plus plus, answer plus plus, and then you just return the answer. This is very easy. Okay. Thank you. This is the last question. So you're given an integer n and a 2D array requirements where requirement of I, it's a pair, end of I and count of I is given. Represents the end index and the number of emergence till that index. We already know what is emergence, I less than j, and nums of I should be greater than nums of j. Return the number of repetitions which follow all the requirements, basically. And we have to count it modulo 10 power 9 plus. So basically, we are given they were given some positions. At those positions, uh, that they've given that this much inversion should be there. At till third position, there should be four different versions or anything like that. They have given different conditions, the requirements. Like let's say till seventh index, there should be 10 inversions like that they were given in the question. And we have to find the total how many permutations of length and satisfy all those conditions. All those conditions, okay. So let's come to this. N is up to 300 only. And there are only at max and requirements and different requirements. And they're given the input is generated so that there is at least I such that end of I equal to inversion. So we have also given the total number of inversions that should be there. That they've already given that EPF and company. Let's say for this question we'll actually have to use a prerequisite, but it's not a prerequisite. It's a quite common DP question. Like find the number of combinations of length n with k emojis. We'll be using that directly, right? And you just have to change a bit in the. Firstly, I'll try and explain that question first. This is just a sub problem. Like you can please change the DP state a bit, and that this should work. So, firstly, we'll come to how to find. We're going to formulate a DP, normal simple DP. Firstly, let's say we'll say DP of n comma k. This is defined as number of permutation. number of permutation of length n of length n with k inversions. We are defining a VP, and now we have to think of how can we do the transitions here. So n is the length of the permutation, and k is the number of inversions that it has, and dp of n comma k gives us the number of permutations with k inversions of length one. So let's think of how can we formulate this dp. How can we do the transitions here is the main question. To think about this, dp of n comma k can be written as dp of n minus 1 comma k. I'll explain how this is working. Just a second. dp of n minus 1 comma k minus 1 up to dp of n minus 1 comma 0. So what does this mean? This means permutation of length n minus 1 with k inversions. Let's say I already have a permutation of length n minus 1, uh, length n minus 1 with k inversion. This has k inversions. Then now I have to put the number n here, right? We have to insert n here, and we should add n should be added. Okay, I'll make it a bit more clearly. That n should be added at a position. Now we already know in this that we needed exactly k inversions. This already has k inversions. So where should I put the n in this permutation such that the number of inversion does not change because it already has k inversions. We need k only. Then we should add n at the end, right? Should add n at the end. Now let's say this has k minus 1 inversions, k minus 1 inversion. Now we want to increase the inversions by 1. We need to increase the inversions by 1 because we want exactly k inversions, and this has already k minus 1 inversions. So we insert the n at a position just before the uh, second largest element, the last element, not the second largest, just the last element, because this will increase the number of inversions by 1. Because n will be greater than any of these elements because this is a permutation of length n minus 1. So we can insert n at the second last position. That will give us uh, like all the permutations with k minus 1 inversions can be converted to permutation of length n with n k inversions like this. So this is basically simply how you can think of this. We will go ahead and formulate this with p. Now with 0 also it is possible. Let's say what is a dp of n minus 1 comma 0? What does this represent? A permutation of length n minus 1 with 0 inversions. That is a sorted one. Only the sorted permutation has 0 inversions. 0 inversions. Right. Now if I want to increase uh, to exactly k, the inversions, then it should be possible that the n minus 1 should be like n minus 1 should be greater than equal to k, right? Why? Because let's say I can only at max increase permutations by n minus 1. I can put the guy like the n element at the front that will increase the inversions by n minus 1. But I cannot increase it more, right? So n minus 1 should be greater than equal to k. This should always hit if you want to fill the DP. Otherwise, it's not possible, right? You cannot make k inversions then. If the number of elements which are already present are already less than k, then how can you make k inversions? At max, you can make n inversions by 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 inserting n at the front. You can make it max n minus 1 inversions, right? So the DP we have kind of formulated how it's going to work. No, it's just this. It's pretty much the same question, just something small they have changed. I'm not going to. I'll explain it through the code. That will be much better. It's very simple actually. If you think about it, what will be changed in the code? They've given that till length, and we should have k inversions, end of I till the end of I index, you should have count of I inversions. They've already given that inversion. So we'll make sure that condition is followed on this, and we'll come to it in a second how will that happen. So let's come here now. Let's look at the code. Uh, so basically, I'll remove this part for now. This part is for the question itself. But firstly, I'm gonna solve the question in another way. Like I'm not solving this question. I'm just telling uh, find permutation, a number of permutations of length n with k inversions. So that we'll go through each length simply, and we'll go to max inversion. Max inversions are always in the reverse sorted permutation. So we can put n here, n minus 1 here, n minus 2 here, n minus 3 here, up to till the n 1. So this will give us n minus 1 into n by 2 inversions. This is the maximum number of inversions, right? You cannot get more inversions than this. So inversion we can take maximum as n into n plus 1 by 2. So n into n plus 1 by 2 will be at max in this question if you think about this. 300, right? So max inversions in this question, it's given in the question, right? So the, the number of inversions we want always less than equal to 400. So we'll keep it till that end. We don't need to actually think of anything else. It's already given in the question that they'll give the number of inversions to be less than equal to 400. So we can keep the maximum number of inversions as 400. So this part will come to it in a minute. Now this is the simple DP. What is going on? DP 0, 0 will state 1. What does this mean? Zero length permutation with zero inversions. There is only one method. That is nothing. There is nothing, but that condition is also like there is one. Right. So the other thing is now we have to insert the next element dp of n comma k. Dp of n comma k is this dp of n comma n minus 1 inv. So we can take dp of len minus 1 plus all the previous inversions. So previous inversion we can say inversion minus position because we can only insert at the number of positions that we already have, right? So if we think about this, we already have a permutation of length n minus 1, right? A1, A2, A3, A4, up to AL. So in this, we can insert at uh, how many places? We can insert at this place, we can insert at this place, this place, this place, up to till n. We can insert at n different places in a permutation of length n minus 1. So for that, I've kept the this thing here. Key how at which positions we can insert. We can insert at the first position. If we insert at the first position, then we'll increase the number of permutations by k directly, right? By n minus 1 directly. If we insert here, then all these and this guy, because it's the n, this is the largest element of all of this, then it will increase the number of inversions by n minus. So we can look at the position. And if the position is greater than equal to 0, that I already told that it must be greater than equal to 0. Otherwise, how can you, like, if there are not that much elements, then you cannot get exactly k inversions, right? If there are less than n k elements in the permutation already, then how can you get k inversions? So this is simply the first TP. What is the question? The question was ki you have to find a length. You have to find number of permutations of length n with k inversions. This is how you can do it. Now the second point in the question is that they're given conditions, right? So the conditions that all those particular nexus must be satisfied. So we'll mark the conditions, and when we do this TP transition, like we are given right at this position, there should be this much amount of inversions. So we'll mark it. We'll keep a map and we'll mark all the positions where we are given that these many amount of inversions are only possible, right? And then if we find this particular length in our marked array, like in our marked unordered map, then then at that place we should only have k number of inversions and count of I number of inversions that they are given. We cannot have any other type of inversions though. Basically, uh, we can also think of it like this, that they have given for length 4, you should have only 3 inversions. Then you should not consider any other permutation like of length 4 with 2 inversions or 1 inversions or 4 inversions or 5 inversions. You should not consider these. You should only consider the ones uh, which has 3 inversions, because they're given in the question that we want at the fourth index there should be at max 3 inversions. So the target we can find as we have marked in the map, right? So we can get the target how many inversions we need at this point. Then all the inversions except that particular inversion, like except that particular value, will set to 0, because we only want the permutations which satisfy this condition always. All others we do not want. So we can mark all others 0, and this current one will leave. So if inversion not equal to the target inversion, how many we want, if it's not equal to that, then we can make all of them equal to 0. And at the end, just we can return for DPFN, for all our DPFNs, we can return the value. So that's pretty much it, actually. So it's quite easy. It's the same question. If you know this question, you just have to change the DP a bit, and you can check it here itself, like above. But you can do it anyhow. It's very simple. But yes. So thank you for watching. That's it.